prove that root 2 is irrational. So to do this, we can use proof by contradiction. So let's first get our assumption, which is the negation of the statement that we have above. That would be that root 2 is rational. A number is either rational or irrational, nothing in between. So root 2 is rational, and a rational number is one which can be expressed as a simplified fraction of integers. And that simplified part is actually the most important bit. So keep an eye out on that. So root 2 is equal to a over b. A and b are both integers. It's a simplified fraction of integers. Let's manipulate this and try and find some kind of contradiction. So we can start by squaring both sides. We end up with 2 is equal to a squared over b squared. And that's useful. Squaring both sides is useful because then we can say that a squared is equal to 2b squared. We've discovered a property of a squared. That means that a squared is even. And if a squared is even, remember that a and b are both integers, so the only way you can square an integer to get an even number is if the original integer is also even. So this means that a is even as well. An odd number squared will not give you an even number. So we can then let a equal to, let's say, 2c. We know that a is even, so let's a equal 2c, and c is an integer as well. So we can denote that with this symbol z here. That means integer. So a is equal to 2c, and then we can put that back into the statement. Actually, I'll put it into this one over here. So 2c all squared is equal to 2b squared. That's 4c squared is 2b squared. B squared is equal to 2c squared. And that means that b is even. So b squared we can see is even as it's a multiple of 2, and therefore b is also even. So we can then let b equal to, let's say, 2d. Root 2 was equal to a over b, and we've just figured out that a is equal to 2c, or a is even, so we let it equal to 2c, and b is also even, so we let it equal to 2d. Let's replace the a and the b with those two things. We get 2c and 2d. And there is our contradiction. A and b are both multiples of 2. They are therefore not a simplified fraction of integers. A over b is not a simplified fraction of integers. They're both multiples of 2. The 2's can then just cancel out. A rational number, like let's say we have something like 0.333, etc., so 0.3 recurring. This, although it's an infinitely long number, it can be expressed as a simplified fraction of integers. But we've just found that root 2, if we set it equal to a over b, when a and b are integers, that fraction will not simplify, because they are both multiples of 2. But then you might be wondering, well, can't we just cancel out the 2's, and now we have a simplified fraction of integers? Okay, let's follow that line of thought. Well, if we cancel out the 2's, and we get c over d, we have a fraction of integers, so we'd end up with, so root 2 is equal to c over d. We can then follow the exact same process. We can square both sides. We can then rearrange and make c squared the subject. We'll be doing the exact same thing as what we had before. And what did we get when we did what we did before? If we set root 2 equal to an integer over an integer, we found that a was even and that b is even. We'll get the exact same thing with this fraction of integers here. We'll find out that c is even and d is even. Or in other words, this will be equal to, or c will be equal to some even number, I'll call it 2e. D will be equal to some even number, I'll call it 2f. Again, the 2's can cancel, and this is an infinite process. So this fraction will never simplify down. Whenever you set it to be a fraction of integers, there will always be a multiple of 2 in the top, there will always be a multiple of 2 in the bottom, and it will infinitely cancel down, implying that there's an infinite set of 2's in here, there's an infinite set of 2's in here, which doesn't make sense. That's not a simplified fraction of integers. It's infinity on top, infinity on the bottom, which doesn't make sense, and therefore root 2 cannot be expressed as a simplified fraction of integers, and therefore it is irrational. Okay, so I've just got rid of some of the stuff which is not part of our working. And now for our conclusion. So a over b, or a and b are both multiples of 2, and therefore a over b is not a simplified fraction of integers.